Hi, I'm Petra Wolf from the University of Trier, and I will talk about how the concept of synchronization can be generalized to push-down automata. This is a joint work together with Henning Fernau and Tomoyuki Yamakami. The concept of synchronization is a well-studied topic in finite automata theory and has been considered for several subclasses of finite automata or different models of finite automata. It has become famous due to the conjecture by Czerny, which says that every synchronizing automaton has a synchronizing word of a quadratic length at most. This conjecture is open for many years now, and a lot of work has been done in this area. The length of a synchronizing word was also the viewpoint of Tomoyuki Yamakami and Aitatsu Mikami, who studied potential synchronizing words for push-down automaton with respect to their length. For push-down automaton, apart from this work, there has only been made very few research on synchronizing push-down automaton. The only work known to us is by Krishikov, Martigün, and Shir Mohammadi, who studied synchronizing automata over nested words. They considered complexity problems over nested word automata, and here in this talk we will also look at the topic of synchronization from a complexity viewpoint. So the models we will consider are first deterministic real-time push-down automata, where the real-time condition says that we do not allow epsilon transitions. Next, we will consider the subclass of real-time counter automata, where counter automaton is a push-down automaton where the stack alphabet is restricted such that we can only put one type of symbols on the stack. Then we will also consider the even more restricted subclass of partially blind counter automaton, where partially blind means that the automaton cannot perform 0 tests during the computation, but it still has to accept with an empty counter. And finally, we will consider finite turn variants of PDAs and DCAs, but we will go more into details here later. As we are talking all the time about deterministic automata, during the talk I will sometimes omit the term deterministic, but we still refer to deterministic automata. So let's first recall what synchronization means for finite automaton. So we call a finite automaton synchronizing if there exists a synchronizing word that maps all states of the automaton to one single state. And the complexity for this problem, so if we only asked whether a given finite automaton is synchronizing, means whether there exists any synchronizing word, this problem can be solved in polynomial time. But if we asked anything more about the synchronizing word, for instance, if we put an upper bound on the length of the synchronizing word, then this problem becomes NP-complete. And if we don't want to synchronize the whole state set, but only a subset of states, or if we want to synchronize the whole state set into a subset of state, then this problem becomes p-space complete. So how can we lift this concept of synchronization to push-down automatons? Well, for sure, we want to keep the constraint that a synchronizing word needs to map all states of the automaton to one single state. But for push-down automata, we do not only have the set of states to consider, but we also have a stack associated with a run induced by word. So we kind of have to deal with the stack contents after reading the synchronizing word. So one option would be to demand that all stacks are empty after applying W to all states of the automaton, which we will call the empty stack model. then we could also demand that all stacks contain the same word after reading W, or we could just say we don't care about the stacks at all and they may contain an arbitrary word or arbitrary words. So the problem we will consider in this talk is the synchronization problem for pushdown automata and other subclasses previously mentioned, where we are given such an automaton and we asked whether there exists a synchronizing word for it in one of these stack contents, in one of these stack models. So as an illustration, consider the following sketch. We have a set of states and we are looking for a synchronizing word W that maps each of these states to one single state. And with each run induced by W, starting in some state, we have a stack associated with this run. So we are still working in a one stack model, but as we are starting on all states in parallel, we have multiple stacks to be considered at the end. So for instance, in the empty stack model, we demand that after applying W on each state, all stacks must be empty, while in the same stack model, all stacks need to contain the same word. And in the arbitrary stack model, they can just contain anything. So how difficult is it to find such a synchronizing word in each of the stack models? It turns out that for pushdown automaton, the problem of synchronization is undecidable, and this is also the case for DCAs. But if we restrict the model even further, meaning if we consider partially blind counter automata, then the problem becomes decidable. And we will now see why this is the case by considering some proofs, and we will start with deterministic counter automata. So for DCAs, the problem of synchronization is undecidable, and we show this by a reduction of the intersection non-emptiness problem for real-time DCAs, which happen to be undecidable. So we are giving two DCAs over a common alphabet. The first one is depicted on the left and the second on the right. And so, for instance, the start state of the first automaton is Q1, and the set of final states is F1, while for the second automaton we have Q2 as the start state and F2 as the set of final states. For the construction, we will add two new letters to the alphabet and three states. So the state on top will be our synchronizing state, where we stay with each input letter and just clear the stack. As we have no outgoing transition for this state, this must be our single synchronizing state. We further add these two states on the bottom here, F1 and F2. These will act as trap states, which will, where the automaton get stuck if we try to cheat somehow. And so what does cheating mean? Well, we now want to make a construction such that the whole automaton is synchronizing if and only if these two DCAs accept a common word. So the first thing we will do is we add a letter A with which we can reset each component corresponding to the DCAs. Because for synchronization, we start in all states in parallel, but for language acceptance, we want to start only in the initial state. So we use the letter A to bring each state of the first DCA to its initial state, and to bring all states of the second DCA to this corresponding initial state. But A will only perform in this way if we see the bottom of stack symbol. If we see anything else, we'll go to the corresponding trap state. This means that if the computation has already started and something has happened on the stack, and we then try to read an A again, we get stuck in the trap states, such that we can be sure that after applying A and not get stuck, we are just in the initial starting configuration. And to see why these states are trap states, if we read the letter A and we see the bottom of stack symbol, then we can leave F1 and F2 into the initial states. But if we see anything else, so if we see a 1 on the counter, or if we read anything else, we stay in the states and add a 1 to the counter. And as we have no transition which erases something from the stack, we are stuck here if we read these states at any time with a non-zero counter. So we now ensured that we cannot reset the automaton at an intermediate state, and that we will start the computation in the initial state and only have to care for the initial state. Because also because the letter A must be the first letter to read, because if we read anything else at the beginning, we would get stuck right at the beginning of the computation. So what is left is that we have to ensure that both automaton are in their final states at the same time. Therefore, we use the letter B. The letter B maps each final state to the synchronizing state, regardless what is on the stack. And it maps each non-synchronizing state to the corresponding trap states and add a 1 on the counter, meaning that we really are stuck because we reached the trap state with non-zero counter. So it's pretty clear that when we have a word that synchronizes this whole automaton, this word will start with an A, meaning that we only have to consider the 2 initial states. And then if we find a word that leads both sub-automatons to the final states, we can synchronize into the synchronizing state, meaning that we have found a word which is accepted by both automatons at the same time. So we have just proven that the synchronization problem for DCAs is undecidable. And as the class of DCAs is a subclass of the class of push-down automaton, this result on top follows. And we will now prove the missing entries of the table, meaning that for partially blind counter automaton, the problem is decidable. Therefore, the decision procedure acts as follows. We have a partially blind counter automaton as input, and we construct from this automaton the Q-fold product automaton. For this automaton, we are no longer acting on single states, but on tuples of states, such that in the ith component of a tuple, the run starting on the state Qi is simulated. Hence, our initial state is just a listing of the states of the original automaton, and our set of final states are all tuples where the entries are identical. Here we no longer are in a counter model, but now we are in a multi-counter model because we have 1 counter for each state. And we are no longer starting in states in parallel, but only in 1 state, but we have now a multi-counter model. And these multi-counter partially blind automaton except by final state and empty stack. So hence it is pretty clear that M is synchronizable in the empty stack model if and only if the language accepted by the product automaton is non-empty, because we start in a listing of all states and we accept if we reach a tuple where all entries are identical. So if we mapped each individual state to the same state. And the latter case, meaning whether the language accepted by the product automaton is non-empty, this is decidable using the reachability problem for Petri nits. But for this problem, this problem has a non-elementary complexity, meaning that this gives us only a non-elementary upper bound on the complexity of the problem. So, and as the multi-counter accepted with an empty stack, we had nothing to do in the empty stack model. But for the arbitrary stack model, we have to clear the stack in the end. And for the arbitrary stack model, we can do this sequentially, while for the same stack model, we have to clear the stacks in parallel in the final states. So as already mentioned, we only have a non-elementary upper bound, and the precise complexity of the synchronization problem for partially blind counter automaton is still open. So maybe we can do better here, but it would be also interesting if this problem really has a non-elementary complexity. So a natural problem to ask is whether we can restrict the model even further to get a better complexity for the synchronization problem. And the idea here is to restrict the stack behavior. For instance, to restrict the number of turns in the stack height profile induced by the synchronizing word. To formalize this, we must first define what a stroke is. So consider a word W and the sequence of configurations induced by this word W starting on some state Q. Then an upstroke is a sequence of configurations such that no transition decreases the stack height, while a downstroke is a sequence of configurations such that no transition increases the stack height. And then the number of turns is the number of alternations between upstrokes and downstrokes. And the problem we are now considering is called n-turn synchronization problem for the considered automaton class, where we are given, for instance, a PDA, and we asked whether there exists a synchronizing word W such that for all states Q, the sequence of configurations induced by reading W starting in the states consists of at most n+1 strokes, or in other words, has at most n turns. So just to illustrate and to make sure that we precisely know what a turn is, consider this stack height profile. What is the number of turns you see here? So think about it for a second. We have some transitions which increase the stack height. We have some transitions which keep the stack heights constant. But we have no transition decreasing the stack height. So here the whole profile shows an upstroke and we have 0 turns. On the other hand, in this stack height profile, we have an upstroke here, followed by a downstroke, again followed by an upstroke. So here the number of turns is 2. So now, can we do better? And the answer is yes. For instance, for one-turn synchronization of deterministic counter automaton, the problem is piece-based complete in each stack model. So for the membership problem, we are given a DCA, and we again construct the Q-fold product automaton from this DCA. But this time we store in each state the seen number of turns. So in each component of the tuple. And again, we have that M is one-turn synchronizable if and only if the language accepted by the product automaton is non-empty. And for the latter case, we have, due to the work of Gurari and Ibarra, there is an exponential length upper bound on the shortest word in this language. And as we are only consider counter automata, which store a number in unary on the stack, we can instead store this number in binary and guess the word in p-space, because we only have to store a binary number with a potential exponential value, but the length of the number is still only polynomial. So this is how we can find such a word in p-space. Now for the hardness proof, we give a reduction from the sync into subset problem of finite automatas, which is we are given a DFA, A, and a subset of states. And we asked whether there exists a word that maps all states of the DFA into the subset S. And the construction works as follows. We add two new states, a check state and a synchronizing state, where we stay with all input letters. And a check state will ensure that we first synchronized into the set S before we can continue to reach the synchronizing state. Therefore, we add a new letter A to the alphabet, which maps all states to the check state, but we will act differently on the stack. For instance, if we are coming from a state in the subset S, then we leave the stack untouched. And as we are talking about DFAs, this means that at this point, we can basically still see the bottom of stack symbol. For states not in S, we will increase the counter, meaning that we put a 1 on the counter. And now in the check state, we will ensure that all paths reaching the state will come from the set S, meaning that we will let these states pass through to the synchronizing state if we can see the bottom of stack symbol. But if we see a 1 which was put on by reaching the state by a state not contained in S, here if we see a 1 on the counter, then we will stay in this check state. And as we have no transition decreasing the stack here, we are stuck because we cannot get rid of this 1 anymore. So this makes sure that whenever we can synchronize this automaton, which means reaching the single sync state, then we first have brought all states into the set S. Now, this was for counter automaton. If we look at pushdown automaton, the picture becomes worse, but diverse, meaning that for one turn sync, meaning that for the one turn sync PDA problem, we have the problem of finding a synchronizing word which only causes one turn is undecidable. Whereas for zero turn DPDA, the problem is p-space complete in the empty stack and arbitrary stack model. So let's conclude with some open problem. As already mentioned, the precise complexity of the synchronization problem for partially blind counter automata in each stack model is open so far. We only have a non-elementary upper bound, and the precise complexity would be very interesting because for me, it's very interesting to see problems which have a non-elementary complexity, really. Then another topic would be, of course, to look for other restrictions yielding a decidable synchronization problem for pushdown automata. And instead, one could also try to lift other related and very natural problems from the realm of DFA synchronization to the concept of PDA synchronization, such as the short synchronizing word problem, where we have an upper bound on the length of a synchronizing word. Because for DFAs, restricting the length of a synchronizing word yields a harder problem because we move from solvable in polynomial time to NP completeness. Whereas for PDAs, this means a drop in complexity because we come from undecidability down to membership in X time. And one could look at whether this problem is really X time complete, or if with some smart trick we could reach p-space membership. And of course, we could relax the real-time condition and allow epsilon transitions, but then we already arrive at some concept of directing word for non-deterministic finite automaton, and then we could also look into synchronizing non-deterministic PDAs. So here is a summary of our results. Thank you very much for listening, and see you in the discussion session.